Hello everyone. I'm presenting our work called Exemplar-based Stylized Gesture Generation from Speech for GENEA Challenge 2022. The goal of this project was to develop a model for generating full-body gestures from speech using machine learning approaches. We planned to design a model which has these main requirements. It should be able to generate realistic animations which fully match the given speech and mimic the stochastic nature of motion. It should be efficient in runtime, scalable with the amount of data, and it should be able to modulate the animation by some style given by the user. We developed a framework for zero-shot style-conditioned speech-to-gesture. Our model is constructed by three main blocks: speech encoder that takes a speech sequence as input and outputs sequence of speech embeddings. Style encoder that takes an arbitrary animation sample and outputs style embedding as a proxy for learned style. And finally, gesture generator that takes these embeddings and generates gesture which matches given speech and mimics given style. Our system is able to generalize to styles that were not covered by the original data and does not require to provide style labels. Although we can still control the styles by labels by simply pre-computing some of our favorite style encodings and using them as labels or tags in runtime. As we mentioned, speech encoder produces a sequence of speech embedding vectors from the audio input. First, low-level features are extracted from the raw audio data. To this end, spectrograms are extracted and projected into the mel frequency scale. Then the log amplitude of each of the channels are outputted. We additionally extract the total energy per frame as a secondary feature. Then, extracted speech features are resampled 30 frames per second to match the frame rate of the provided motion files. Finally, we have the neural network parts, where extracted features are passed through 1D convolution layers, followed by nonlinear operators, and followed by a frame-wise linear layer. The kernels of the convolution layers are set to create a receptive field of about 1 second of speech. The style encoder produces a fixed-size, low-dimensional embedding vector representing the motion style of an example clip. We used a series of 1D CNNs followed by a bidirectional GRU and a linear layer which outputs the parameters of the posterior distribution in our variational autoencoder structure. Using variational autoencoder posterior modeling provides an efficient way to have a better disentanglement in the style space and also injecting stochasticity in the generated gestures. Gesture generator is an autoregressive model which in each step takes current pose and speech embeddings and generates the next pose. For each iteration, the output is denormalized and the root transform and also the facing direction is updated. We use a fixed target facing direction to avoid rotational drifting. To integrate the style embeddings in the gesture generation process, we used feature-wise linear encoding in different parts of gesture generator. As for data preparation, we noticed that the training data contains long periods of silence, low volume audio, cross-speaker audio bleeding, speaker data with little to no hand gesture motion, and noisy finger motions, all of which could hinder model training. To address these issues, we removed long periods of silence in the recordings, given the timestamps in the speech transcripts. This process also removed longer sections in which an interlocutor is speaking, causing audio bleeding into the recording. We normalized the loudness of all recordings to address low and varying volume audio sections. Regarding animation data, we identified and removed the samples with low average hand velocity, which would result in a static generated gesture. In addition, we removed finger motion data due to finger motion quality, which would lead to unnatural looking hands. There are a few details to mention about training process. First, during training, the conditioning style example used for training encompasses the 128 target frames, but is extended by surrounding frames from the source animation code. The number of surrounding frame is chosen randomly to create a sequence of length m spanning from 128 to 256. We did not use any teacher forcing or noise scheduling during training. This made the training a little bit slower, but achieved much better results with no mode collapse. Framing our model as a conditional VAE, the objective is to maximize the evidence lower bound of the marginal log likelihood of gesture motion given a speech sequence. For the reconstruction loss, we use different motion characteristics in both local and word space, using a differentiable forward kinematic block. And finally, here are some test results generated by our model.
I like any kind of music except for like screaming. I don't do that. Oh. Nope. Will you? Yeah, no, I wouldn't. But I used to go to concerts all the time. I've been to my favorite one was Matt. He sings "Come On Get Higher." I like any kind of music except for like screaming. I don't do that. Oh. Nope. Will you? Yeah, no, I wouldn't. But I used to go to concerts all the time. I've been to my favorite one was Matt. He sings. God. You did? God. You did? Where'd you get it from? Okay. Oh my gosh. Oh, perfect. Yep. And you know what? They'll probably actually be better than the actual breeders because they won't. Yeah. Oh my god, I'm so excited. I love your life. That's amazing. We like to kayak. In the summer, I really, really love kayaking. Yeah. We should go kayaking next year. I love to kayak. And we like to do stuff outside, but I don't enjoy working out at all. It is like, I hate it. I really do hate it. And he literally hates me for hating it because I'm like, I'm going to the gym today. He's never going to.
Thank you for your attention.